In this installment, I want to introduce the idea that integration can be thought of as an addition operation. My intended audience for this installment are students that might not have seen calculus beyond the first term college calculus, and so probably did not see integrals in much depth, if at all. Here, I want to give you a way to think about integration conceptually, and the goal is not to learn how to actually perform an integration. Really, I just wanted to demystify integrals and give a way in which students can approach learning material in which integration is of fundamental importance. Keep in mind that my presentation here is entirely clouded on my memory of the calculus classes that I went through. The standard calculus curriculum is broken up into 3 terms, with some exceptions. The focus of Calculus 1 tends to be derivatives, while integrals are often not introduced in earnest until Calculus 3, with a class sandwiched in between that seems to be a prep for advanced math classes. At least that is the sequence I had. It is unfortunate since this sequence gave me the idea that integration is a more advanced concept than derivatives. However, there is no reason to view them that way. In fact, after a whole slew of math classes, I've come to see integrals as somewhat more basic and intuitive than derivatives. Nevertheless, let's start with reviewing derivatives and then move on to integrals. Derivatives are introduced as slopes. By that, what we mean is that if we have some function and we choose some point, say x0, then the derivative of that function evaluated at x0 is the slope of that function at x0. In other words, the slope of a straight line smacked right onto the curve at x0. And just a reminder that the slope of a line is defined as the rise of that line over some run along the x-axis. Now let's jump to Calc 3 in our first take on integrals. For me, integrals were introduced as antiderivatives. So after 2 terms of studying derivatives, I was told simply that the operation of an integral undoes a derivative. Mathematically, that is a perfectly true statement, but at least for me, did not give me a very good foothold for how to think about integration conceptually. So take 2. We are taught that an integral is an area. Specifically, the integral of a function from a to b is the area under the function extending down to the axis. And this is also true, and does give a conceptual way to think about integration, but there's actually a better way to parse out what integration is. So that brings me to take 3 on integration, and that is that integration is summation. So let's imagine that we sum the value of some function at a bunch of points. Here, those values are indicated with subscripts on the f, but it is really the same function, just evaluated at different points. The standard notation we use for summation is the capital Greek S, and let's just make a lazy, less sinuous s, which becomes our integration symbol, and replace our summation symbol with that integration symbol, adding another bit that I will get into in a bit. And what we get is that integration of some function is just a summation over that function. Okay, let's jump back to Calc 1 and re-look at derivatives as differences along a function. Although this is not how derivatives are typically introduced, that is what they are. Let's take our function, and I will use the somewhat common notation del sub x to indicate derivative with respect to x. And we can approximate that derivative by considering some point x sub I plus 1 and the value of the function at that point, each minus some other value x sub I and the function value at x sub I. In other words, we are approximating the derivative is a ratio of differences, with the numerator the difference of the function evaluated at the 2 points. And this ratio is just the rise over the run, which can be a good approximation of the slope of the function over this interval. And we do not use the symbol del just arbitrarily. It is like a lazy version of the Greek lowercase d, d for difference. Contrast that to the last slide, where s was for sum. Okay, let's try to get more specific on our integration as summation interpretation. As I've said, an integral of a function from a to b is just the area under that function from a to b. But let's approximate that integral with a bunch of rectangles with constant width, where the height of those rectangles matches the function. So for instance, in this rectangle centered on x2, That is the value that we evaluate the function at, and that gives us the height of that rectangle. And then the width is delta x, which we need to choose. And in that manner, we break up our integral into the summation of the areas of a bunch of rectangles. So really, I should say integration is summation of a bunch of discrete bins along a function. Anyway, so we can imagine filling up each of our rectangles with some elements, here pictured as disks. And then our integration is the sum of how many of those disks fit in each of the bins. And this counting of how many things fit in each bin might remind you of a histogram. And that is the main conceptual point I wanted to arrive at here. And that is that we can think of integrals as summation over histograms. This interpretation will allow us to conceptually consider probability mass functions and probability density functions the same, and that both can be related to histograms. But I'll save further thoughts on that for later. So to sum up, every time you see an integral, just keep in the back of your mind that it is nothing more than a summation. Replace the function with a histogram that fits under the function, and add the number of elements in each of the bins.